Next, let's solve a more complicated circuit with the three methods. The circuit still includes a unit impulse current source and a zero-state capacitor. The complicated part is a parallel resistor R. Firstly, we solve the integral from 0 minus to 0 plus. To list the circuit's equation, we should list the KCL equation on this node. Then we know C times duc over dt plus uc over R equals Is equals delta t. This is the only equation we can list from the circuit. By integrating this equation from 0 minus to 0 plus, we know that C times the integral of duc over dt from 0 minus to 0 plus 1 over R times the integral of uc from 0 minus to 0 plus equals the integral of delta t from 0 minus to 0 plus. We know this is 1. Similar to the previous discussion, because the capacitor is in zero state, we also know it equals C times uc 0 plus. Now let's analyze this one. What does it equal? We should think about the integral of uc from 0 minus to 0 plus. Is it possible that from 0 minus to 0 plus, uc is the infinite value? That is the impulse function value? You can think about it. It's impossible. Why? If uc is the infinite value or an impulse function, then ic and duc over dt is a much sharper function than the impulse function. But in circuits, we don't describe the derivative of delta t. As exercise 1 shows, the fattest change we can accept is the instantaneous jump of the capacitor's voltage as a consequence of moving the unit charge caused by delta t. Similarly, the inductor's current may also have an instantaneous jump. In other words, in real circuits, UC may have an instantaneous jump or IL may have an instantaneous jump, but they cannot be infinite values. It means this may be an instantaneous jump from 0 minus to 0 plus, but the integral must be 0. So we get that UC 0 plus equals 1 over C. When t is greater than 0, the current source is a zero-value current source. In other words, it's open. This circuit becomes a zero-input circuit. We need to point out the condition of this current is after t is greater than 0 plus. For this circuit, with the three elements method, we can easily get UCT equals 1 over C times e to the power of minus t over RC, and t is greater than 0 plus. ICT equals minus 1 over RC times e to the power of minus t over RC, and t is greater than 0 plus. Now we still haven't finished the solution. In this circuit, these two expressions are correct only when t is greater than 0 plus. When t is from 0 minus to 0 plus, UC changes from 0 to 1 over C. According to the differential relationship between the capacitor's voltage and the current, we know IC equals C times duc over dt equals delta t. So we can draw the waveform of the capacitor's voltage. It jumps from 0 to 1 over C at t equals 0 and decays to 0 with a negative exponent. IC is a unit impulse function at t equals 0. When t is greater than 0 plus, it decays from minus 1 over RC to 0 with negative exponent. This is the result we get from 0 minus to 0 plus integral. The second method is observation. We suppose the capacitor's voltage keeps constant from 0 minus to 0 plus. In other words, the capacitor is equivalent to a short circuit line. This is the equivalent circuit of the given one. Obviously, in this resistive circuit, IC equals delta T because it shorts the branch and all the current flows through it. So our supposition is wrong. Then UC 0 plus equals 1 over c times the integral of IC equals 1 over c. This conclusion is the same as that from the previous discussion. When t is greater than 0 plus, we still need to solve a zero input response. The whole analysis is the same as the previous one, and we won't discuss it again. The third method is to solve the unit step response. Now we need to draw the unit step circuit. We know the steady state value of UC must equal R, so we can get UCT equals R times 1 minus e to the power of minus t over RC times epsilon t. Similarly, IC plus 0 plus equals 1, and IC steady state equals 0. So ICT equals e to the power of minus t over RC times epsilon t. These two expressions are the unit step responses ST. Because HT is a derivative of ST, we can solve the unit impulse responses of UC and IC respectively. UCT-HT equals the differential of R times 1 minus e to the power of minus t over RC times epsilon t. We can find there are two terms with t, so we need to differentiate them respectively. What's the first part? It equals 1 over c times e to the power of minus t over RC times epsilon t. The second part equals R times 1 minus e to the power of minus t over RC times delta t. This is just ft times delta t. For this function, f0 is 0, so it equals 0. This is the expression of the unit impulse response of UCT. Next, we will solve the unit impulse response of IC. ICT equals the differential of e to the power of minus t over RC times epsilon t. There are two terms with t, so we write them out respectively. It equals minus 1 over RC times e to the power of minus t over RC times epsilon t, plus e to the power of minus t over RC times delta t. This is another ft times delta t. It equals f0 times delta t, and f0 in this function is 1. Then the unit impulse response of IC is delta t plus minus 1 over RC times e to the power of minus t over RC times epsilon t. By comparing the three methods, you will find the sum of two parts in the first method is just a result of the third method. So the conclusions of the three methods are the same. We need to point out that from the aspect of the solution, there's no doubt that the second method is the simplest. If you want to use the third method, in the step of differentiating ST for HT, ST should contain epsilon t. In other words, t is with the entire time axis during the differentiating. And in the differentiating process, we often need to use the property that ft times delta t equals f0 times delta t.